Yeah, good evening. Good evening. Okay. Can you hear me, students? Hello. Very good evening, good afternoon. Yes, yes. Okay. Got it. Thank you. So let's start. We are proceeding. Yeah, good evening, good afternoon as well. So we are proceeding with machine learning. We did certain linear regression also, okay, with the Boston House data set. So when we are working with a linear regression, we know that what is a straight line equation. And for this, we had used a scikit-learn. Okay. And inside the scikit-learn, we had called linear regression class. So directly, basically, this is available. Linear regression class is available inside scikit-learn linear model. And inside it, there's a linear regression class. We had already used entire linear regression, and we have seen how the fit method and the predict method is working. Inside the fit method, we can send the data for the training, and during the prediction method, we are sending the data for the testing. So testing data is being sent into the predict, and inside the fit training. So in fit, training is being done, and in predict, testing is being done. Okay, so this is there. Now, if you remember, during when we are working on the scikit-learn, so we need to check it out, the scikit-learn matrix as well, because matrix convey us the responses that convey us the model performances. So for the model performances, I had told you three basically: mean squared error, mean absolute error. These are the same means here, and RMSE, root mean square error. And there is one more R2 score, R square you can call it. So these convey you the errors, and this will convey you that how much change is coming whenever input variables are being changed. Okay, so that one is a R square. So this much adaptation we have to check whenever we are going with a linear regression. Okay. If you remember, I had also told you, like when I'm testing any numpy array, inside the numpy.array, I had sent it out certain input data here. I had sent it out into the comma separation. In a number of variables, number of input data, I had sent it out. So I had just did t dot reshape as well. Why I'm doing the reshape here, I'm telling you that I'm sending you one row, and I'm sending you -1 many columns. So these are many columns, many. So many columns, so one row, many columns I'm sending to you. And now this should be predicted. So if LM is the instance here, oh, LM.predict. LM.predict method, inside it, I'm sending this T. Because my LM model, which is a linear regression model, has been trained on 2D data, two-dimensional data, which is coming from data frame. So it is trained onto the X and Y. So that's why 2D data we are giving it here. If we are taking directly T, suppose here itself I am directly putting lm.predict, and here I am putting this T here. So that will throw the error of one dimension. It said we need a 2D. Okay, so this is there. So remember, whenever we are doing the reshape method is inside the numpy. So T itself is a numpy array. So reshape method will take rows and column. So if I'm writing here one row -1, it means one row, many column. And if I'm writing here T dot reshape, T means it's a variable holding the value. It could be any other variable, does not matter. If I'm writing here -1, 1, so it means many row, one column. So we need to adjust it. So here I'm just giving this one, that I'm sending you one row and many column. So this we did it here. Now what you can do. Okay, so here I'm taking one more case study. That one is related with, here again, this is related with almost, you can say, real estate case study. Here, one is making a like building. Okay, so let me tell you here, wait, let me find out. Okay, there is very popular website here, very popular website, which is used for taking out the data set. That one is UCI Machine Learning Repository. UCI Machine Learning Repository is a global repositories handled by UCI University. And here, there one can find out a lot of data set. So here, if I'm looking here, data sets, browse data set, a lot of data sets are there. Hey, from here, UCI Machine Learning Repository, there is one of the data set, very popular data set, concrete compressive strength data set, it is there. So here I'm just calling it UCI Machine Learning Repository, concrete compressive strength. Concrete compressive strength data set is there. So here I'm opening it inside the UCI Machine Learning Repository. So here you can read it, the details. The documentation details are given here. Okay, documentation details are given here. Concrete is the most important material in civil engineering. Concrete, through which you are making a building. Okay, so concrete is the most important material in civil engineering. The concrete compressive strength. So we need to find out the concrete compressive strength by mixing out the materials. There are, whenever a building is constructed, there are a lot of materials are required. Got the point here? We mix not we, means the people who are making the building, builders and their employees. So they mix a lot of material, 4 or 5 materials together. Okay. So their concrete strength is highly required to maintain the building actually. So here, it is a physical science subject area related with it. We can do the regression task here. So here it is saying that what is the data set information? Number of instances are 1030 rows are there because we are requiring a lot of data sets. We are requiring a lot of data inside the data set. So number of rows or instances are 1030 rows. Number of columns or attributes are 9. Attribute breakdown, it is saying there are 8 quantitative input variables. So X is 8 input variables and 1 quantitative output variable. That one is Y here. Okay. There is no missing attribute. There is no missing attribute. Just wait. Okay, additional variable information. See here. Given the variable names, variable types, and brief descriptions are given here, the concrete compressive strength is a regression problem. So here it is saying, let's say the name of the data, the name of the, here, the name of the input columns are cement, which is the input variable, cement, blast furnace, fly ash, water, super plasticizer, quartz aggregate, fine aggregate, age of those material, or concrete compressive strength. So here, when you look these one, so they are X. X is the input variable. And this one is coming as the Y as the output here. Okay. Okay. So X and Y. So we'll be taking all these as an input variable and this one as the output variable. Okay. Now, if we talk about the data set here, this one is a data set you can see here. Download is the place from where the data set is there. Okay, so maybe this file is coming into the XLS. So you are not going to download it from here. You are going to take this data set from my GitHub. Okay, because I just downloaded it and just change it into the CSV file because earlier the data set is coming with the XLS. So here download, but direct downloading is from here, but currently you can take the data set from the GitHub. All the data sets are available into the GitHub right now. Okay. Okay. So here I'm just, you can go to GitHub and you can load it. So here I'm loading this data set. This one. So I just loaded this data set here. Import NumPy, Pandas, scikit-learn.linear model, import linear regression, sklearn.model selection, import train test slate, and visualization libraries and warnings are loaded. I had loaded this data, concrete data.csv. This file is there. You can just go to GitHub and from there you can load it inside the Jupyter. So concrete data.csv is there. I'm loading it into the data frame here. You can see this one is a concrete data.csv. So if you check it out, there is a cement, blast, fly ash, water, super plasticizer, CAFA. These are the names which I've shown you into the dataset information and the age. So these are all X values, and the CMS is the Y, which is a label or which is a target you can consider. So this one is concrete compressive strength. Now, means here, see, the point is here now. If one is mixing different material or creating a building, so there are standard mixtures are required, standard amounts are required to make the mixture to get the concrete compressive strength, which is required as a standard concrete compressive strength to make a building, a particular building where one is making the building, means in which place, what strength is required as per the ground is there. So here machine learning is helping that one can think it that if these different mixtures are provided, so what would be the concrete compressive strength, or they are as per the standard defined by the government for any building strength as well. So from here only one can check it. So this is easy now. Earlier it was not there. Okay. So, okay, so X and Y, you received it here. So 1030 rows and 9 columns I am having here. Okay, data.shape here, because we are doing the EDA. Whenever we are loading any data set, we need to do the EDA, exploratory data analysis. There we need to wrangle the data, there we need to understand the data, we need to find out the insights of the data, we need to do the feature engineering, feature selection, data cleansing as well. So entire process is required. Data.shapes here, 1030 rows and 9 columns are there. Data.d type. So here data type here. Here it is showing all the data types here. Floats are the data type and age is integer. Data.info. So here it is showing that what are the information. There are total 9 columns are there, 1030 entries are there, and there is no missing data, and what are the data types. So entire information it is giving to you. Here it is showing data.columns. Here it is just showing you the description, statistical summary. You have to find out here observations that what this actually statistical summary is conveying to you. Here we are checking it out, outliers are there or not. So you can just check it out, outliers are there. Here some outliers are there in age. And we can even find out this box plot individually. So whenever we are taking individual one column data, we call it a univariate analysis. And here I'm taking the entire data into the subplot here so that we can see all the 8 input columns details here. So from here, yeah, we are getting a few are having the outliers. Very few data are have not much outliers are present here. Is there a null data? Here there is a no null data here. Let's find out the correlation, that how much the data are correlated with each other. So here it is just saying that see carefully. I told you, you need to check out the colors. So the color which is moving this side, they are highly positive. The colors which are moving this side, they are negative. So negative correlation and the positive correlation. So here you can check it out. Like see this one. This is completely white and this one is black. So negative correlations. So it means water and superplasticizers are negatively having the negative correlation with each other. If you see carefully here, these. See, this 1.33 is mentioned also here. So some colors are moving here. So here we can say, yeah, there is a positive correlation between age and concrete compressive strength. Okay. Now here you can check it out. This one is a concrete compressive strength. You can see which input variables are highly correlated with CMS. Cement is highly correlated with CMS. If more cement is there, so concrete compressive strength is very high. Same superplasticizer is also correlated and age is also correlated. Rest are okay. There is not negative correlations here. There is no black color coming here. So there is none of the input variable is working as a black, working into the very negative correlation. That is not there. Now we are checking out certain skewness into the data. So here into the age, it is just showing. Yeah, when we are doing the univariate analysis, yeah, into the age, it is just showing the this skewness is there. Okay, just we are checking out the histogram. So here it is checking out that what is the distribution here. Now here it is checking it out because the skewness is present there. So we are trying to find out, we are trying to remove the skewness here. So and numpy.log transformation method we are using to remove the skewness. So one can use the numpy.log transformation or box, any of them one can use that. Now we are looking here, it is skewed. Now here it is coming into the normal distribution. Okay, there are others also, means here you can see there are others distribution plots also here I'm making. This one is normal distributed now. Even we can use the for loop where we can just take all the data columns here and all the distribution plot we can make it here for all the columns. All the 7-8 columns here, we can just take it here. So here it is just showing, yeah, some are normal, some are little skewed are there, some are normal. So wherever some skewness is there, you can remove with the numpy.log transformation. Rest are okay, rest are normally distributed, they are okay. Okay, so the point is here, more EDA process, one can use it, more visualization, one can use it. Now here I want to segregate the data into the input and output variables so that we can send the data to the machine learning here. So here, first of all, how can I take out the data? Like here, this is your data set. Okay, how you will be dragging it out? Because inside this entire data set, this one is your X data, and this one is your Y data, X, Y, this one is CMS. So X is equal to D, this one is the data, na? So same data frame name. You can give any name, that is your choice. df.ilog here, you can give me all the rows and give me column starting from 0th index up to -1. So -1, this CMS will be automatically eliminated. So I'll be getting the input data I'm having. Now, if I need a Y data, output data, so the data is the data frame name. You can take any other also, whatever name you're choosing here. Now, here, ilog function, give me all the rows and -1 column. So I will be getting a CMS. Okay, so this is there. So X and Y are dragged here. Okay, so X and Y are dragged here, and you can see Y is equal to data.ilog. This line number 20 is taking the output data Y. This one is the CMS, and Y.shape here, 1030 rows are there. Into the X here, this one. Okay, in this way also you can write it. Students, you can write it any way, like data.ilog. This will also work. This will also work. Or this will also work. That's okay. You need the data, X data. Both will work. Okay. So here into X, it is just showing all the input data. Input data you are having now. Okay. Okay. Now come here. You can see shape. 1030 rows and 8 columns are there. And into the Y, 1030 rows are there. So the point is here, you are having X and Y collectively. Now we need to make the split. Split. See, when you're making a split now, you can give this, just wait here. Wait. This one. This is your X data. This is your Y data. I'm splitting it. So you can, suppose here I am given test size 0.22. So it means 20%. You can just consider it as 20%. So you can give it a 220 also. That is also okay. So it means 80-20%. So you can give here 20. So directly that will come. 20 will come. Here, if I had given 0.22, so here it means 22% will go to the testing, and yours 78% will go to the training. It does not matter. You can give 20. That is okay. So train data, test data. So here X train, Y train, X test, Y test. Okay. Now we are taking this data here. I'm sending this X, Y into the train test split. So input and output I'm sending. So these two I'm sending. And sending the split this X and Y into the 20% training testing and 80% training. Now, what is this random state? Random state is the seed value which will be selecting, the rows which will be moving towards the testing, and the rows which should be moving towards the training. I will be giving more detail about this one later on. Just you need to wear. Here we can take the, I'm already slow. I'm already taking my pace. This much pace is required. Now here you can see, like we can say outliers. If you talk about the outliers, you should add that stage also. But inside this data set, there are very few outliers, if I say. There are very few outliers. That's why I just skipped it. But when you are doing that, you can add that stage before this splitting, you can add that. Okay. So here, once we are splitting it here, we are getting X train, X test, Y train, Y test. So all these four we are returning. Means here, this train test split is returning this X train, X test, Y train, and Y test here. Okay. Now you can check it out, X train dot shape. So here it is just saying X train dot shape. So that one is a 803 rows and 8 columns. Into the X test dot shape, that one is 227 rows and 8 columns. In Y train dot shape, that one is 803 rows are there and single column. If it is not given, automatically it is one column. Y test dot shape, it is 227 rows and one column it is there. Okay, done. Now, after that, I need to do the machine learning. So I need to call linear regression. LM is the instance of that. You can make any other instance name also. Now I'm doing the training. During the training, I'm just using lm.fit method, and inside it, I'm going to send it out X-train data and the Y-train data. So here I'm sending. So here the model is coming to the training here. So training is being done. Once it is ready, your this training is done. We can check it out, the score here. This one is 81. So 0.81, it means 81%. Currently, the model LM is working perfectly. So these are the coefficient values here. Various coefficient values coming here, some negative, some positive. So it is saying that these coefficient value will be added or subtracted into the Y whenever unit change is coming into the independent variables or input variables. This one is an intercept here. You can see here. This one is an intercept coming here. Okay, this one is an intercept coming here. After that, once my training is over, then we can just give this predictions. We can do the validation by giving certain data. So here I'm giving the X-test data to the lm.predict method. I can just send it X-test data. Okay, so prediction is there. So here I'm sending the test data, and here it is just predicting it. So prediction is coming here. Now here we are checking it out, all the predicted value and the actual value. So predicted values are given the machine answers, and Y test is the actual answer. So actual answers and the machine answers are there. Machine answers are there as well as actual answers are there. Okay, because now here we can see predicted value and the actual value. So you can see these values which are coming now, these are the predicted values, and there are the actual values also. So you can see here, there are so many values here coming because there's a lot of data. That's why so many values are coming. So suppose here, if I take the predicted value, see here, suppose here I'm taking this value, suppose 45.94. So 45.94 is there. And here, what is the predicted value here? That one is okay. That one is here. Nearby value. So 45.94, this one is, it is saying 52.91. These are the actual one. So 52.91. So it means here it is saying 45.94 is nearby 46 approximation. And here it is saying 52.91. So basically it is saying these are the machine answers, these are the machine answers, and these are the actual answers here. Okay. So because here it is saying 81.81 is the score coming here. So here it is saying 81% correctly it is examining the output. Suppose here I'm saying like this 1, 2, 3, 65 is there. So what is the third here? 74 it is there. So at one stage here it is saying that whenever any input is given, some concrete compressive strength value will be 65 point something and actual value is 74. So this can happen. Some variation could be there because this is just a machine, but these are the machine given answers and these are the actual answer. Still your machine is doing very well because they are giving all the answers nearby here. Okay. So these are, we are doing the validation. It's fine. Now here, Okay, I need to check it out the errors as well. Okay, I need to check it out the errors as well here. So here you can check it out that from sklearn import mean squared error. So you can see here. From sklearn.matrix import mean squared error, R square error. So when you are doing, you can call mean absolute error and root mean square error. Okay. So here I'm just calling mean squared error. So here I'm just giving the predicted data and the actual data. So here it is just giving me certain errors, mean squared error it is giving me. Okay, even you can write here just you can find out the R square also. The code you can just take it from load Boston data, the same matrix you can trace it here. Okay, now what I can do, I can just make the prediction. I can just make a function to predict the value. And how we can do that? For that now, here I created a separate function so that this function could be called once only. Means here once I'll create a function. So as many as time I can call it with the different values of input. So here I just given predict test function. This is just a name, user defined function I created. So DEF predict test function. Okay, here I'm going to send out the test value. Inside the test value, I'm going to pass input variables. How many input variables? 8 input variables. I'm going to send it out because LM model has been trained on 8 input variables. So same number of columns or variables I need to send. So here it is np.array. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 input variables I need to check it out into the NumPy array, and this I'm sending inside the prediction test, this particular user defined function. Now here we have to be careful because right now what is happening, this data which I'm sending, so this test V is one dimensional. Okay, it is one dimensional only. So I need to send it into the 2D. So once I send it now here into the test V with predict test method here. So here you can say test value dot reshape. I used it as a reshape, and here I'm saying this should be changed to 1 row many column. 1 row many column. Then test value is there. So lm dot predict test value. Okay, so lm dot predict test value, and here it is giving you the prediction. So it means if these are the input variables values, so the concrete compressive strength will be this one, 29 point something. So in this way we do ML of linear regression. Okay. So this is about the linear regression, okay, where we are having the output into the continuous output. I'm having continuous output. Okay, so let's come to the next now. Now, when we talk about the machine learning, now you are aware with the supervised. That in supervised learning, there is a must presence of Y variable, Y output variable. When we talk about the supervised, further two categories are there you came to know about. That one is regression and classification that you know now. When we talk about the regression, linear regression, you came to know that inside the linear regression, the Y value must be present into the form of decimal value. Okay. Now there is another one, logistic regression. Logistic regression. Whenever my output variable, which is Y, is coming into the two outputs only. Yes, no, no, yes. Means only two outputs. Yes, no. True, false. 0 or 1 or 1 or 0. So the point is that in these cases, we are having logistic regression. Okay, only logistic regression. So whenever I am having categorical data into the form of binary only. Binary means only two data I am having, two outputs I am having, nothing more than that. So in that case, I should be moving towards the logistic regression, we can say. So here you can see here in okay, just wait here. Here, what we did in concrete compressive strength, we use the machine learning. In concrete compressive strength, we use the machine learning, okay? And by using the machine learning, we are predicting that what would be the concrete compressive strength if we are giving different input variables. Got the point here? So initially we had trained with these data, this entire machine learning means here, we did the entire EDA, we did the entire process of machine learning, I did it. And then finally, I just split the data into the training and testing. And here during the linear regression, I call the model linear regression. And I use the fit method where I'm giving the training with the above data set. And then I'm giving the newer data set. Means here I'm giving the validation to the linear regression model by providing the X test data, where the testing data here I'm sending. And then here, we are giving, once our model is completely trained and been working on the newer data set, means X test data set, then we are giving the new values to the LM model, to the linear regression model, and asking it kindly tell us that what would be the concrete compressive strength. So here we are giving the newer value newer 8 input values to the model and asking the LM model just predict the new concrete compressive strength after providing the newer value. So here it is giving us the new concrete compressive strength, that this would be the concrete 299.6 will be the concrete compressive strength if you mix this material in these proportion. If you mix all the 8 input material which is required for civil engineering into these proportions, your concrete compressive strength will be 299.60. So here one can match it out whether this is a standard concrete compressive strength is required to use inside the building or not. So machine learning is required to predict the new value based on to the input value. This one is there here. Okay. This is there. Okay, now you can see here. Okay, so here we are looking here. Suppose here when we are talking about, suppose here, see, if my data are in this way, suppose my data are this one, you consider. So here it is possible that linear regression could be working. Linear regression could be working here. Okay. Fine, because we are having this equation here. This equation is working for the linear regression in such type of data points. If my data points are spreaded in this way, so we are having here y is equal to a plus bx plus e. This one is the equation which is following here. Now, when we talk about here, so you think it's suppose I'm having my data spreaded in different mode. That one is spreaded in this way. Some of the data points are lying here and some of the data points are lying here. So in this case, if I started using the linear regression, so how my lines are moving? My lines will start moving in this way. So if my lines of straight line will move in this way, so my model is not learning anything because onto the straight line only 2 points are driven. What about the extra point? What about these extra points here? So the point is here, this is not feasible. Linear regression is not feasible in such type of data whenever I'm having this data here. Either here I'm having my data or here I'm having my data. Now, here, what I'll do, if I use instead this way or this way, this is much better. So the point is here, some of the points are coming into the 0 zone, some of the points are coming into the 1 zone. So I'm having only 2 values, such as 0 and 1 only, that's all. So here, direct linear regression will never work. Here, this type of work could be handled, means here, all the data points are coming on this line. So basically, this is known as logit. Or we call it a logic also. Logic means logistic regression. Logistic regression, where I'm having only 2 logics, only 2 values I'm having, 0 and 1. So here linear regression that is giving the straight line equation, that will not work. What the point here? Right? So that is there. Okay. So when we talk about, just wait here. When we talk about here, this particularly logistic regression. So like if you remember, like y is equal to a plus bx, that one is going for the normal linear regression. But when we talk about the logistic regression here, my equation is changed, but actually that is also a kind of linear regression. But here, because direct sequence we do not have here for straight line equation, that is not possible in any case. So here, the changes will be made here, and this logistic regression will be creating the equation in this way. Log of p over 1 minus p, because here we are having only two values, only 0 or 1. Only two values, 0 or 1 values we are having. Okay, success or failure means only two, true or false. So only one value will be there, one value will be here. So that is equivalent to y basically. But in linear regression, we are having y is equal to a plus bx. So here y is equivalent, this is equivalent to y basically. Okay, and this y is what? This y is basically, you know, a plus bx plus e. Okay, but here in logistic regression, this will be working. So here, when we talk about logistic regression, here we are having log of p over 1 minus p. Okay, this is equivalent to y. This is equivalent to y. And y is already, you know, y, this y is what? This y itself is what? That one is your a plus b, b1, x1, b2, x2, bn, xn, and goes on, plus b. This one is entire equation for this one. So here we can say log of p, this one is equivalent to y here. This is y, complete y is here. Okay, so in case here, suppose here I'm just shifting this log towards this side. So here this will become 1 over 1 minus p is equal to exponent of y. This will become here. Okay, ey here. And here, if I want to find out this p value, p is what? P is the probability value here. So if I want to find out the p value, so 1 over 1 minus p, I will do it here. So I will be getting 1 over ey, because here I want to find out p here, probability is here. So here 1 by p, this one is 1 by p, I'm taking 1 by p here, minus 1 over 8 here, ey here. I'm just shifting this one here. Okay, and if I need this y, this p, I want to calculate. What is this p? This is a probability value actually. And inside this y, there's a complete equation for a plus b1 x1 b2 x2. That one is there. So complete y is there for the a1 b1 a plus b1 x1 b2 x2. That is there here. Okay. Okay, so this probability is calculated. Now, what is this p here? P is actually now, this p is probability value. So actually, what happened? Whenever we are talking about the linear regression here, sorry, logistic regression here. So here default there is a threshold value given, because this above value is considered as a 1, the below value is considered as a 0. So here what happens, if there is a threshold value of 0.5, there's a threshold value of 0.5 here. Okay, so what happens when this probability value is calculated internally by given all the input variable onto this equation? So if this probability value is greater than 0.5, so that particular output falls into 1. 1 means high. If this probability value is having lower values to 0.5, so that particular output value will be falling into the 0 zone. Now, here, once the values which are falling into one zone and the value which are falling here into the zero zone, how we can understand now that suppose here I'm having a data set, you consider I'm having a data set which should be having the values of suppose I'm having a diabetic data set, diabetes I'm having. So inside the diabetes, okay, the values which are falling here into zero zone, so these are non-diabetic people. When their medical values are treated, so they are find out with no diabetes, they are okay. With zero, there is zero diabetes, with no diabetes. And the values, the data points which are falling above side, these are all diabetic people. Okay, so diabetic and non-diabetic. So only two values are there into the data set, either the diabetes or non-diabetes. So 0 or 1 values are there. Okay, when this we can understand. So this all is being done just with the help of logistic regression. So whenever we are having the output, my output into the 0, 1, 0, 1, yes, no, it's only two values I'm having. So there I can just consider here your logistic regression here I can consider. So here I'm going to take one of the healthcare data set here. I'm using a healthcare data set where it is going to show you whether the patient is having a cancer or not here. So we are going to do the cancer detection using machine learning. So this one is itself is a healthcare data set. So here the entire details of the data set is given. Sorry, here is the entire detail of the cancer is given here. Now here, inside this data set, we are having input values, input variable values. So here we are having all these values such as you can see radius, texture. So, okay, this data set is related with the breast cancer. So here we are having this particular data set inside the scikit-learn. So I will be taking this data set and we are detecting whether the person is having a cancer or not here. So these are the input values here, such like the radius, texture, perimeter, area, smoothness, compactness, concavity, symmetry, and other things are there. So here it will be conveying you whether the person is having a cancer or not here. So here I'm going to load the data set. So here, first of all, I need to call all the libraries. Okay, so I am calling logistic regression. So what I do here, I'm going to write it. Just wait here. This one is the same one here, Sandra. Same. Which I had explained. This one is the same here. This is the same which I had explained. Okay. Wait here. Let me write here. Which data set I'm writing. Okay. Here I'm going to find it out. Wait. Here sklearn. See here, logistic regression is there. Class sklearn.linear model, logistic regression is there. There are several other parameters inside any of the model. So they are just working as a default. So here I'm just calling class sklearn.linear model, import logistic regression here. Okay. So this one is a cancer data set. Related with the logistic regression. Okay. So here I need to import a lot of libraries basically. Inside the linear mode, logistic regression is present. Execute it. So all the libraries you have to call, and still matplotlib and other libraries you need to call. It is just executing, it is trying to call it here. Okay, in the meantime, let it be calling here. So once it is called here, so here, let's say DS is the data set. I'm going to take it. That one here, I'm going to load it here. Load. This will be loaded. Let it be coming here. It is still executing actually. This is there. It will be showing to you. After certain time, you need to wait here. If we are checking it out, ps.keys, it will start showing you the keys here, which is data, target, feature names, all these things will be showing. What is happening? It is taking a lot of time. Just wait. We need to wait. The star is coming up. It is executing. It is loading the file and it is bringing those files into the Jupyter internally. Okay. That is there. It is executed. One is coming, two is coming. So all the things are executed. Here it is showing you DS. Data is what? These are all, you can see here, data. These are the input variables. These array are NumPy array. These are all the input variables. No, there are many input variables. I'll be checking. Now here target. Targets are coming into 0 and 1, 0, 1, 0, 1, 0, 1 only, because this is a logistic regression. You will never find out continuous value. Like if you remember target, when you checked it out, Boston House data set, there is a target coming like 24.2 for 2.6. In that way, the target is coming, but here the target will be coming into the 0 and 1, 0, 1, 0, 1, 0, 1. So target here, so here it is showing you whether the person is having a cancer or not. Okay, so this is there. These are here, it is just showing number of instances. 569 rows are there and number of attributes are 30 numerical attributes are there, 30. Here, there are a lot of names provided here. What are the input variables are there? These are all input variables. But we can check it out here. Feature names are provided here. You can see the feature names provided here. Like here, you can see all the 30 input variables are there: mean radius, mean texture, mean parameter, mean area, smoothness, compactness, concavity, errors, a lot of things, parameter and a lot of, so 30 input variables. These are all input variables. Okay, input variables. These are the details of input variables. These are the target 0 and 1, and these are data here. So here I'm going to call it ts.keys. Here it is showing me dataset.keys, data, target frame, target name. These are the keys here. So here what I'm going to do, here I'm going to call them one by one. So here I'm writing ds.data. So data is, it is going to show you only data, only data. Data means input variables. ds.target. Target means here it is showing the target number. This target it is showing. So this is target. These are target. Okay. If I want to find out the feature names here, so feature names I can take it. ds dot feature names here. So these are the feature names here. Okay, 30 input variables are there. Fine. These are there. So right now I'm just looking into the NumPy array. What I do here, I'm going to put it. Suppose because I had called the pandas also above, I had called import pandas as PD. So here I can call it df. Df is what? Data frame I'm creating. You can just write here cancer also. This one is a data set. Then whatever name you want to give it for the data frame, that is your choice. pd.data frame, and here you can give input variables. So input variables are ds.data here. So I can take ds.data. So here you can just provide what is the data variable. So here one can provide ds.data. Okay. And here we can just write columns are ds.feature names here. So here it is just showing you all the input variables, ds.feature names, and these are the data provided. So all are coming into the two-dimensional data, means here X and Y formats you are getting here. 569 rows and 30 columns are there. So these are there. Okay. Okay. So these are there. Now here, ds target is there. So here we can take ds.target. So the target is here. These are coming into 0 and these are the targets. So this I can take it directly. Oh, it is a DS cancer, you know. The name is DF cancer, data frame cancer. So you should know the name here. DF cancer, otherwise it will throw the error. DF cancer. So you can see here. So one more output variable has been created. Target. So here you can see 0, 1. 0, 1s are coming here. These are the targets here. These are coming here. These are the target 0, 1, 0, 1. 0, 1, 0, 1 is coming here. So these are the targets. Okay. Now, once, so you are having an input and output here entirely, right? Okay. Now here you can just try. Okay. Right now, DF cancer, we are having this entire data I'm having. Okay. So DF cancer dot head. DF cancer dot tail means here if you need to do entire ETA, that is a work, you can add here. So a lot of reading you need to do it yourself there. Okay. Data types, we are checking it out here. PDF answer of detailed info. You can just check it out. What are the informations here? Okay. So you can just check it out. There's no null values here. And a lot of EDA you can just trace out on your own. Okay, all the regression, everything you can do that. Now here, what I am going to do, I am going to take out the data because here right now, if I take it out DF answer. So here, I need to track out X and Y data to split the data. In between, a lot of EDA processes required. You can add it later on. Here, I want to take out the data which is coming for the X and Y. So here, last column is for target. So that when I can take it into the -1. So here I'm just dragging it out here. X is equal to DF cancer dot log. You need to track out your variable names, otherwise it will a lot of errors. Here colon, making -1. X. No, it is 0 to -1, 0 to -1. So here I'm getting X data. So here only input data I'm getting, all the input data here I'm getting. So you can see here, last data, all the input data here I'm getting. Now Y. Here I can get okay. So I received Y here. Now I need to do here train test split. I need to split the data. So these values will be returned X train, X test, it is test, X train, X test, Y train, Y test is equal to here test size. I need to give test size. I can give 80, 20 or 30, anything you can give it here. So suppose that I'm writing 0.20, it means 20% will go for the testing and 80% will go for the training here. Random state. Random state is a value. It is 42 actually. Random state is a value, basically, it is a seed value. Random state is a seed value which provides that which rows should go to the testing and which rows should go to the training. That work your random state is doing. Okay. Now here, X. Oh, I'm just taking out the shape here. But here it is showing that these row numbers are provided here. These rows are used for training data. So here I'm just looking, what are the shape here? 455 rows means because total of 569 rows are there. So 455 rows and 30 columns are chosen as training. One 14s are chosen as testing. Okay. So this is there. Now I need to call this logistic. So splitting, I did it. Now I need to call the logistic regression here. This is the logistic regression. Okay, wait, I'd already called it. So this I need. Okay. So I'm making the instance of it. So suppose the logistic regression LG, I'm making any variable, you can make it here, and logistic regression instance we are making. LG.fit. Okay. This is just coming as certain warnings are coming here. So to suppress this warning, what I can do, at the beginning of the code, I can add, here I can add import warnings. Warnings is there now. So that pink lines are coming with the warnings. I want to suppress those. Okay, it is trained. Now here I'm writing LG dot predict, and inside the predict I can send the X test data. Which data? This data, X test. This one, X test. So these are the testing data. Okay. Done. Okay. I can hold this prediction into the variable. Some 0101 values are coming, whether the person is having a cancer or not. Okay. So up to here, we are just training at the testing here. Now, what about the model performance? How we can check it out, how well the model is working? For that, we are having a separate matrix. We are having a separate matrix in case of logistic regression. So now we need to check it out, those separate matrix here. So just wait, I need to take out the separate matrix. Now we need to understand what are the separate matrix to for checking out the this particular logistic regression model performance here. Okay. Just wait here. Just wait for a moment, student. Let me take out one document here. You need to wait for certain time. I just stopped the share. Let me find out one document here. Wait, student, just wait. You need to wait. Wait for some minutes. My files are. Just give some time. Okay. Okay, got it now. Fine, just. Okay. Hmm. Now, what we can do, see, when we talk about logistic regression, because here my data is moving into the categorical one. Means here I'm getting a data into 0 and 1. Okay, either the values are 0 or it's 1, true or false. Means only two values I'm having. So in that case, my metrics are different actually. Okay, metrics. In case of logistic regression, the metrics are accuracy score, confusion matrix, and classification report. These are the three basic metrics which are required for logistic regression. Okay. So accuracy score, confusion matrix, and classification report, these are required here. So how these will work basically? If you remember, during the statistics, I had told you about the confusion matrix. The same matrix is going to be used here also. So here in, let's check it out how these matrices are going to work now. Okay. So see, basically now, what happens, like when I talk about the confusion matrix, let's say, suppose, let's say, suppose here I'm having some values. Suppose I'm having, let's consider, I'm having 500 rows. So during the 500 rows, I'm just predicting cancer. You think it, I'm taking case. So here, the values which are lying here, the values which are lying here and here, they are the right values. And the values which will be coming here, this portion and this portion, they are detected as the errors here. Error and error values. So let's say here I'm having a 500 rows, and if I'm making a confusion matrix, this is a called as a confusion matrix, and let's say I'm getting the values of, let's say, 100 here, no sorry, 400 here, and I'm getting 100 here. So how can I interpret it? It means out of 500 rows which are sent for the testing, 400 people are detected that there's no cancer, 100 people are detected with cancer. So here I can just check it out, this particular diagonal. And currently there is 0 error, 0 error. So it means all the 500 rows either are coming into the yes cancer or no cancer case. None of them are detected into the error. Now I'm changing the situation here. You think it out, suppose. Then I send the data for the prediction. So here, the values which are coming here, suppose here I say out of 400, I'm getting 390 values here and 10 values are lying here. So it means 10 values are lying, 10 values are lying here. And here, 90 values are lying here, and here 10 values are lying here. So here, what does it mean? It means that 390 people are detected with no cancer, 90 people are detected with cancer, but here 10 people are still detected into the errorful cases. Error cases means here that these people are falsely detected and these people are doubtful cases. 10 people are having, we are having a doubt that whether they are having a cancer. Basically, these people should come into the no cancer state, but still they are falsely, they are detected. There's some of the symptoms are detected as having a cancer. So this comes into the error zone, okay, because these are the doubtful cases. Same is happening here, such as 90 people are detected with cancer, but still 10 people are detected as they are having the symptoms of having no cancer basically, but they are falsely detected here. Means here these 10 people should be present here inside the 90, inside the people who are having cancer, but somehow they are carrying the symptoms. That is also saying that maybe these people do not have a cancer. So it means some of the people, these number of people should move towards the 90, but currently they are coming into the doubtful stages. So this is there. Okay, this is there. So this is a confusion matrix here. So here we gave certain technical name to these segments. So here we call it a true positive, and this one's a true negative, false positive, and false negative. Okay. Now, when we talk about accuracy, suppose here we are talking about accuracy. What is accuracy? Accuracy means that we can detect these values, the values which are coming in these two zones divided by overall. So it means 400 plus 100, the values which are coming in these two zones divided by overall. So you are getting what? You're getting 1. So accuracy is 1. So it means if my all the values are lying into either this zone or either this zone, and here I'm getting the value zeros. So that means here the values are coming with 1. Means here there is no error detected, and all the values are coming here as a 1. Means here your model, I can say your model is working perfectly, and it is detecting all the provided value carefully. All the provided value carefully here. Okay, this is there. In this way, we need to understand this data. Now here, I'm going to take, let's see this now. See this carefully now, and I'll explain now. Read it carefully first. What is this? So here you can see, this is a confusion matrix basically. And you can see how the values are given here. What are the names given here? This is true positive and this is true negative. It means all the positive values are lying into the true positive area and all the negative values are lying into the true negative area. And this one is a false negative and false positive here. So what does it mean here? It means that the errors are lying here and the values which are showing inside the false positive and false negative here. Okay, the values which are coming into the false positive and false negative here, they are the errorful values. They are the errorful values. Okay, if my values are moving into the error, so my accuracy will be down. Suppose here you think it, like earlier I had given the 500 rows we are sending for machine to predict. So here, like here I'm writing 400 coming here and 100 coming here. So all 500 are consumed here. So it means there is nothing, 0 here, 0 here. So what will be the accuracy? If all the values are lying into the true positive zone and true negative zone, so nothing error is there. So here you will be getting true positive. Here 400 plus 100 divided by true positive, here 400 plus here 0 value plus 0 value plus 100. So you will be getting what? 1. So your accuracy is 1. And if your accuracy is 1, it means your performance is 100% correct. Your model is predicting all the values 100% correct. And whenever you are having any values here, either here or here, so it means your accuracy is coming down. Suppose here I'm saying like 490 here, so 10 are moving here, or 90 are here and 10 are moving here. So it means the values are moving into the false negative and false positive also. So automatically 10 values are coming here. So you are not getting 1, you are getting some another figure. So it means your accuracy is little bit down because some of the values are coming into the error zone also. And these error zones are coming if some of the people are having a symptoms of cancer, or here some of the people are having, there's no symptoms of cancer, they should be moving into the no cancer state. So these are certain doubtful cases. So they are all moved into the doubt cases or error cases, doubtful cases or error cases here. Okay. There are certain another, just to see these value carefully now. Here you can see how other things are calculated, because when we do the matrix in case of logistic regression, so here first of all we need to check it out the accuracy score also. Then here confusion matrix is the same one with this one is a confusion matrix. Okay. And then we need a classification report. When we need the classification report, so inside this report, here we'll be getting the matrix of various different aspects, such like the accuracy, okay, you can see the formula working here. Recall of sensitivity here, true positive over true positive plus false negative, true positive. What are the actual true positive, or what are the total number of true positive? Because the values which are going here also into the false negative, they should be considered into this true positive. But here these are doubts. That's why the values are working here into the false negative. So recall or sensitivity say that what is the ratio that the values are coming into the true positive, okay, across total to true positive, because these values also should fall here, but due to the certain symptoms, they are coming into the error zone here. Then there is a precision. You can see formula here, true positive over true positive plus false positive. This also shows that what is the ratio here that the values are actual true positive, because the values which are lying here, they should also move towards the true, because here what happens, that here, if I say like 490 patients are not having any cancer, 10 are doubtful, and here it is saying that 90 people are detected with cancer and 10 are doubtful cases. So here it is saying there are two things here. Here it is saying that these 10 people are having, they are not having, why they are doubtful? Because these 10 people are not having a symptoms of cancer, but they are completely doubtful cases. Means one is not assured with these cases, because if directly these 10 people are put here, suppose here into the true negative, so these people are also cancer. So doctor will start treating with the cancer, that doctor will start giving a cancer treatment to these 10 people. But the point is here, machine is saying that we are not sure with these 10 people that these are having 100% cancer. Maybe they do not have it. So means a kind of a error or doubtful cases is raising here. So that's why it is coming here. So precision is giving here true positive or true positive plus false positive here. So precision is saying here that what is the ratio of actual true positive over the total true positive in this case. Specificity is just showing that what is the ratio of actual people having the true negative over total true negative values here. So basically, now we are having a F1. F1 is showing you the model performance, which is saying you that one is F1 is equal to 2 into precision plus recall over precision into recall over precision plus recall. That one is a F1 complete model performance. Okay. So this one is the entire classification report here. So F1 is the model performance, 2 into precision into recall divided by precision plus recall. So this shows you the actual model performance, how well the model is working. Okay, so accuracy score, confusion matrix, and the classification reports, we need it here. So these all are working for your matrix. So I need to call this matrix here. I'm calling this matrix here. sklearn dot matrix import confusion matrix classification report and accuracy score. You can just call it. Wait. Here you can call it. We are having a library here. Okay, so I'm calling it here. So I had imported it here. Na? So prediction and Y test I had created. Y test also I had created and prediction values. So here I'm just calling accuracy score. Here I can give the predicted value and the Y test value. Accuracy score, it is showing me 0.96. 0.96 means 96% my model is working correctly. So 96% is well and good. Okay. Print. Here also I can send it. Okay. Here it is saying, wait, this one is a confusion matrix. Here we can understand it in a way like, can you see I have 40 and 1? So here you can just understand in this way. Here it is saying 40 cases are with no cancer, 70 cases are with cancer. 40 people are diagnosed as no cancer, 70 people are diagnosed as with cancer. There are certain doubtful cases with 1 here and 3 here. So it means if I'm taking the same figure, actual and predicted. So here in actual, it is saying 40. So 40 is, patients are diagnosed with no cancer, they are okay. But here it is saying one person, here one person is detecting with cancer. This, it is an error, doubtful zone. And here 70 people are detected with 70 people are detected with yes cancer, but still 3 people are diagnosed with doubtful cases. So these are the actual values, accuracy values, but these are errorful zone. 3 here and 1 here, these are the errorful zone. Okay. Okay, so in this way, so these diagonal you have to take. Okay, so this one is no cancer, yes cancer. Okay, and these are errors that can happen. Okay, now here I need to take here it is detecting the values which are coming here now. Just wait here. Wait here. Here, print. See the classification report here. Here you can see like the values which are coming into the classification report. It is saying that we had sent 114 total number of rows for the prediction purpose here. 114 total number of rows for the prediction purpose here. Where out of that 0 are total 41. 41 rows are towards the 0 side with no cancer. 1 are there with yes cancer. 73 rows are just showing you the cases of yes cancer. People are having cancer. But the point is there how well the model is detecting them, whether they are having a cancer or not with the error. So here it is just showing you that because here when we draw this confusion matrix is going to show you here the actual cases and the predicted cases here. Okay, into the confusion matrix. So here all the values which are 0, which are where actual and predicted both are matching, that will be moving here. And all the values which are same with the one case with yes cancer in actual and the predicted, they are predicted here. So here it is just showing 40 cases we had find it out with no cancer, 70 cases we had find it out with yes cancer. But here the values which are reflected here. Okay, so like 1 case is here or 3 cases here. So these are what? These are the error cases. Error cases or the doubtful cases which are coming here. These are the errorful cases or the doubtful cases. So here the doubt is that this actual cases are with no cancer, 40 people, but this one person is detected as some of the symptoms of cancer, maybe they are having, but the model is not assured 100%. So that's why I'll throw this one value into the this zone, errorful zone, doubtful zone here. But this should be here, but it is not actually given here. The same is having the 3 cases here, that maybe these people do not have a cancer, like these are having cancer, but maybe a possibility these 3 people are not having a cancer. A complete doubt zone is there. So that's why it is throwing it here. So here, these are doubt cases. 1 and 3 are doubtful cases. So total are 41 this side and 73 are here. And the total 114 rows we had sent it out for the testing here. So here model is detecting these cases, but just to detect like all the 41 cases here, some of the F1 score here, it is saying like, you can understand like F1 score, if we check it out, that 95% correctly it is working for the 0th and 97% correctly it is working for the 1, because some 3 cases are coming into the error. But if I take overall average, not individually for this or this, overall average we have to check it out, that is nearby 96. So accuracy average is 96%. So basically F1 score or accuracy show you the model performance here. So it is saying in overall your model is performing, overall your model is performing 96% correct. And if the model is working 96% correctly, so it is well and good. This is very good, your model is working. Okay, so in this way, my model is working, right? Got the point here? So in this way, we can work with here. For the logistic regression, you need to make a logistic regression fit, predict, and accuracy score. So these are all basically metrics we have to check. So in regression, if I talk about the linear regression, the metrics are totally different. In case of logistic regression, the metrics are totally different here. Okay, so these are there. See here. Just wait here. This one is a cancer detection. You can just see it here. I just load it. Here I had taken a different variable here. Here you can see there's a logistic regression. There's no beta. These are the value. These are all libraries. I had called it here. I had loaded it here. But here in this file, I just created a separate variables. Variable means different variables. I just called it here. Means the name of the variables are differently taken. So whatever name you are taking, you are need to tracking that here. It's a logistic regression. Keys here I'm looking, values here I'm looking here. Descriptions, these are just descriptions here. These are the feature names. So I'd given a cancer set as a name and I'd loaded it here, target here. Keys, I'm checking target names, data shape here, I'm checking it out, putting them into the data frame here. So whatever variable name you're taking it here, you have to track out and trace out there. Here I'm doing a small area only. There's a target variable, just I'm using a count plot to see the target variable, how many are like 200 rows are given to 0 and 350 rows are given to 1 into the target variable. Just looking at correlations here. This here entire EDA, you need to stretch it out. Now here I'm, okay, here I'm taking the X in a different way. So in this way also you can do that. Like here I'm dropping the target to take the X. Like there I'm taking X is equal to df.ilog function, I'm taking it here. But here I'm taking in a different way, df cancel dot drop target. So target will be dropped along with column. So X I'm getting. This is also a way to take out the X, or df.ilog operation you can take, just like in last file I did. Any of them you can do that. In this way also I can take the target variable Y here. Anyway, whichever is comfortable to you, you can think it ilog function or directly also, that is okay. Shape here I'm doing it. Splitting of the data I'm doing it here. Shape here. Here I'm just checking it out, test X values also. So like here it is just saying 440 number row, 260 number row, 260 number row, 145 number row, 504. So these are just coming for the test X. Test X dot shape. Logistic regression, I'm going to call it here. Zero fit prediction, I'm going to do matrix, I'm checking it out, accuracy score, confusion matrix, and classification report. I'm just looking here, confusion matrix in this way also. Okay. Let me take out one file. Just wait, please. Yeah, you have to do the entire EDA. You can do that also. Okay. So here now what I did, once the LG model has been trained, now here I just created a cancer predict function so that there I can give a values, new values, and ask whether the person is suffering from the cancer or not. So here I'm just giving these values. So here you can take like cancer predict function, and here I'm writing, I'm sending the value of B. Here I'm reshaping it, And inside the edge.predict, I'm just giving the value of P. Here, predict print, predicted value, prediction is there. And we are writing if prediction is equal to 0, if my prediction is coming to 0, it means the person does not have a cancer. And if it is coming 1, so the person is suffering from the cancer. Now, when we are giving it now here, so you can see here, P is equal to np.array. Here I'm giving like here I'm giving 30 input variables here I'm giving. These all values which I'm giving, 30 input variables I'm giving. 30 input variables I'm giving and sending into the cancer prediction. So once it is just sending here into the cancer prediction P, so here it is P. Okay, so here it is just checking it out P. Here it is saying the person does not have a cancer. Okay, so if whatever answers are coming at 0, so it will be saying if the person does not have cancer, and if you're getting a 1, so person is suffering from cancer. So in this way, we can do the logistic regression. Now, let me tell you one thing, like here now, when I'm doing it, so let me tell you the random state now. Random state is a value here. See here, random state. Random state. So random state, it is just saying you, like I had given a 42. So basically random state is a seed value. This is a seed value. This seed values gives you, this seed values gives you the numbers. This seed values will give you the numbers. What numbers it will be giving you? Just like suppose I say you are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the row numbers of any data set. So if seed value 42, it is giving you highly, it is going to take those rows which are highly correlated. So those rows it will be sending for the testing, and rest of the rows it will be sending for the training. So suppose seed value 42 is going to say that row number 3, row number 5, row number 8 and 10. These row number 3, 5, 8 and 10. These rows should be sent towards the training. These rows should be sent towards the training. Sorry, these rows, these rows should be sent towards the testing. Sorry, these rows sent towards the testing. So random state is a seed value which will be selecting the rows which are highly correlated and sending it to the testing. And the remaining rows, like here, 1, 2, 4, 6, 7, 9, these will be sending to the training. And these are selected in a way where we will be getting a good results. Okay. Suppose here I'm just saying random state 42, it is there. Random state 42, it is there. And let me check it out. What is the accuracy score coming? That is, one is a 96 here. Now, suppose, let me think it's okay. Can I improve this 96 to 98, 99 or 1? So what I can do, I can just settle down this value of random state to any other value so that I can make a trial that whether I can move ahead to 96. I can move ahead to 96. Like, can I go to 97? Can I go to 98 or 99 or upside? So I can change this random state. It will be changing this. This is a seed value. It will be selecting a different rows, which will be moving to the testing, and the remaining will go for the training. Okay. Let me check it out. So wherever my random state seed value is giving me upside for the accuracy score, there I will be staying. And if it is going downside, I will retry another value. So if I check it out, accuracy score is 95, so it is reduced. Okay, so I'll just change it. I'll try some another value. But here with 42, 96 is coming here. So 47, let me try here. So this test and try, we can do that so that we can check it out which one is giving us. Oh, it is coming downside here. 93, it is coming downside here. So here I can check it out. Any other value, let's say suppose I'm writing here 50. Means I'm trying. Oh, it is 50 here. Because the best values of the best seed values will be selecting the perfect rows for the testing that is coming between 43 or 42 to 51 or 52. So we means these values can be tested first of all. I can test it out. This is coming 94. So here now it is moving maximum 96 with 42 only. So otherwise I'm coming downside here into the EQ. So I will be coming back to the where I'm getting the higher side here. Like, so with the 42, I'm getting the so here it is giving 96. So now with the 42, I'm getting the 96. So I will be staying with the 42. Even means here test and trial from 42 to 51, 52, we can do that, or 55. Means majorly I've seen the values which are coming from 40 to 50 or 51 or 52, they are giving the best. These different seed values are giving the best best accuracy score by selecting the different rows which are highly correlated into the testing. Okay. So that's all for today. Thank you very much. Thank you. Thank you. And when you are doing, you can add the AD on your own, all the kind here.